Welcome back to our course. We're going to, in this submodule, discuss inverse trigonometric functions. Now, the idea here is that our normal trig functions like sine, cosine, tangent, cosecant, secant, and cotangent take as inputs an angle, and it outputs to you a ratio of sides of a triangle. So what would an inverse function to this look like? Well, it would input a ratio and output an angle. So we're going to define trigonometric inverse functions based exactly on this principle. So to reiterate, recall that trigonometric functions input an angle and output a number based on ratios of the sides. The inverse trig functions will do the opposite. They'll input a number and output an angle. So what kind of notation do we use for this? Well, the school of thought that I subscribe to that is more common is to say the inverse function of sine is arc sine. The inverse function of cosine is arc cosine. Sometimes you see other notation. You might see sine with a -1, something like this. But arc is a bit more universal, I believe. So what does it really mean to be the inverse function? Well, recall what it means to be an inverse. It would mean that when I apply the sine function to arc of x, I recover the original input x. So let's try to understand this. So my claims are as follows. Arc sine of 1/2 is 30 degrees. So what does this really mean? Well, let's draw a picture here. So if I have this picture for a triangle, computing arc sine of 1/2 is asking what is theta here? What angle will give me sine of that angle equals 1/2? And the answer is 30. So this is just equivalent to saying that sine of 30 degrees equals 1/2. It's just a way of rewriting it. Similarly, sine of square root over 2 is just like saying that sine of 60 degrees is equal to square root 3 over 2. And then arc sine of 1 is like saying sine of 90 degrees is equal to 1. And this last one here is like saying that sine of 0 degrees equals 0. So if you have a hard time remembering things, keep in mind that it's totally equivalent to just remember the important values for the sine function. You don't necessarily need to memorize the values for arc sine. They can be derived from each other because they're inverse functions. Of course, the same principle applies to all of the other 5 trig functions. We don't necessarily need to write them out in this lecture. The exact same principle applies. So just as an example, suppose you were asked to find arctangent of 1. Well, what does this mean? This means I should have an angle, and that angle should have the property that when I take the tangent of it, I get 1. So this is the angle theta such that tangent of theta should be equal to 1. So what's the picture here? I want to have a triangle whose opposite side and adjacent side are equal. So why is that the case? Well, because tangent is opposite over adjacent. If I want that ratio to be 1, I need them to be equal. So this is our, of course, isosceles right triangle. It's equal leg lengths. So this is, of course, the case when theta is equal to 45 degrees. But also we should know it in radians as pi over 4. So let's just do a couple quick exercises with computing inverse trig functions. Arc cosine of 1. So this is equal to theta such that cosine of theta is equal to 1. Well, do we remember when cosine is equal to 1? Well, that's when theta is equal to 0. Now, I will make a remark at this point, which is for those of you who are really understanding what's going on here, you might say, well, if I'm just looking at theta such that cosine of theta equals 1, theta equals 0 is not the only choice, because cosine is periodic. In fact, it is 2 pi periodic. So I can use 2 pi, 4 pi, 6 pi, or really I can write it compactly as 2 pi times k for k an integer. So in general, you can think of the inverse trig functions as having many possible outputs. But it's difficult to understand because I want it to be a function, which means one-to-one output. So I had this issue where to sort of define an inverse trig function that respects the periodicity of the original trig function, well, the inverse trig function should be multi-valued. It should be able to output many different angles. But that violates the definition of a function. So the way we get around this is by restricting the domain of the inverse trig functions. And we'll look at this in a later submodule. There are many different ways to restrict the domain, but mathematicians have come up with a canonical way to do it. So I will describe that canonical method in later submodules. So let's look at another example with arctangent. So first, we will find one angle which satisfies the desired property, and then we'll use periodicity to say, well, not only is it that angle, but any sort of other multiple of that angle, potentially. So let's look at the picture here. So I want to know what angle what angle is theta. Because arctan of square root of 3 is equal to theta such that tangent of theta equals square root 3. In other words, i.e., opposite over adjacent equals square root of 3. And this happens in the 30, 60, 90 triangle when theta is equal to 60 degrees. Or pi over 3. But again, we have the periodicity of tangent. So not only will pi over 3 work, but so will any multiple of pi. So I can add k times pi for any integer k. So why is it pi and not 2 pi? It's because tangent is pi periodic. So it repeats more. So in some sense, I want to say that this is the correct answer. That there's just one output, and then all of the other ones are the same up to adding this concept of pi k. But I need to discuss how to restrict the domain and range of inverse inverse trig functions in order to make this notion precise and make them honest to goodness functions.